I've got h is I take my cost function, I divide it by v to the t, multiply the discount factor, and so on. And I will stick a little 0 here to indicate time, because we're going to assume we have a stationary version of the Markov chain. And I have to have a stationary Markov chain realization with an infinite interval backwards and forwards. And here's why. This PT is a conditional expectation of C into the future, right? That's something about the future. I haven't seen the future yet. We want something that's causal that involves going back in the past, and that's why we're going to assume we have X for all time. So at time T, I observe the minus infinity up till now. So this is pretty easy now because I plug that in and use the fact that what? I use the fact that the expectation of, we've done this a few times now, this is definitely fair game in an exam. That's a conditional expectation, right? Okay, so by definition, that is equal to that. And that F0, that's conditioned on everything up until now. So not just the guide comes in.
How did I miss that first line?
What's that?
The first expected value is the continuation of, it's not equal to what's above it, you're saying?
Wait. This is B.
You're just
that's
plugging
H.
in. Okay.
I'm taking one, so I want to take this and plug it in.
Okay,
I
at
don't want
times
to
at
throw all
times
that
zero.
in once. Eventually, I'm going to multiply this by beta to the T and the sum.
What about the beta?
Yeah, what can I throw it away? I'm saying that if I plug this in, I get a whole bunch of terms. There'll be betas, as you say. But this is the kind of thing, these are the things that are complicated. I mean, I could multiply both sides by beta to the T. Oh, no, I'm saying, let's analyze this. This is the difficult thing. That's a definition. That's a definition. That's a thing that concerns us. Because we have a product of that and something like beta and BC. The sum is no big deal, the beta is no big deal. The problem is we will get products like that, and that's what's bothering us.
Okay, I see.
Yeah. And that's equal to the expectation of psi vector C of xt. Okay? Because I can take this inside the conditional expectation, and again use the same thing that I use over and over and over again. The derivation of Q learning, splits down by blah, 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 the smoothing part of the conditional expectation. This goes inside, and the expectation of conditional expectation. And then the magic in blue. There you have it. So by basically assuming stationarity, I can shift time by backwards by t. And the big thing is causality. Now this is the past, not the future. That's the value here. This thing in here involves predictions of the future. Now I've got something in the past. And so we can plug this back in. And we get a formula for B. And now you don't have to worry. I'll multiply by beta and I'll put everything in. there. So I took the sum in. All right, there's nothing here, there's no content. There's one master stroke right there. And now I'm just adding things up. So here I put it, I multiply by beta and summed it, like we said we would. Shifted time like I said I would. And now I took the sum inside the expectation. You know, and I can do that if things are bounded, say, whatever. Just or positive or whatever. And if it's under conditions, I can do that. Does that look familiar? It's my basis functions put through a first order low pass filter. It's TD1, that's the eligibility vector.
Shouldn't the second sum go from negative infinity to 0?
Yeah, it should, but I have minus 2. It's the same, yeah. I'm going back.
Okay, I see, I see.
Yeah, I had a sum from 0 to infinity, I kept, and I could switch to 0. It's much easier just to keep it, just plug in, let's plug in. And so B turns out to be the inner product of the eligibility vector, you know, and maybe it's better, right, like a BI is the ith component of the eligibility vector, MC of x0 for every I. And so why is that TD learning? Let's,
Wait, hold on.
yeah.
If you're shifting the t's now,
Yeah.
inside of that,
Mhm.
wouldn't that change the t and the beta though?
No, just look at the
Minus
algebra.
T.
No, all I did is algebra. I said, I plugged in H here, and I said it's really annoying, I've got a psi times P to the TC. Do you agree with that? Yeah? And then I said, well, that's a conditional expectation, and I got that. So there's nothing but substitution. There's nothing but substitution. So I'm keeping this from 0 to infinity, which is no problem.
Yeah, so what I'm seeing is that you shifted everything by
No, but
minus t.
go step by step, that's a fact.
Yes.
That's a fact, because I'm allowed to move this any way I want. You know, all I did is I subtracted t from there and t from there, that's a fact. Yeah, so it's fine. And then taking the sum inside. You know.
But if you subtract t on the inside,
What?
so you do a shift of t, so you
No, no,
rescale t.
it's only inside the expectation. No, it's
You're
I'm
not
using
doing it on the outside?
stationarity. No, it's stationarity. This expectation, if xt is a stationary process,
Okay.
then I can shift this any way I want. I could, you know, subtract out t, subtract out t.
Okay.
So, you know, it's probabilistic, it's not, you know, and which is something.
I'm not seeing how we got rid of the conditional expectation.
Well, that's the smoothing property again. So, I mean,
Yeah.
I take this inside because it's known,
The
and
law
I
of
have an
the rate of
expectation,
expectation.
expectation, and that's always the same expectation.
Sorry, can you say that again?
It's called, this is a smoothing property.
Right, and so you're taking the sign side.
Yeah. So it's always true that the expectation of any variable g given
Yeah.
that's always true. That's always.
Okay, and it's okay that, because what's confusing me is we have c of xt given at 0.
Yeah, but this is zero measurable, so I'm taking it inside.
Right, okay, but c of xt isn't at 0.
Yep, either is g.
Okay.
Yeah.
Okay, so when you brought in the sum inside
Yeah,
of bt,
yep, just algebra.
so what are we that expectation is with respect to what filtration? Because I see
No,
a
no,
zero
no
and
conditional
negative.
expectation. I used conditional expectation once in order to do this shift. There's no more conditional,
Can you
there's no
only just-
conditional expectations.
But you can only bring bt inside as measurable in whatever filtration that expectation.
No, no, I've got a formula here. I mean, this is this, fact.
It's okay.
This is this, so
Beta is
so
a
I don't have to worry
constant.
anymore. I've done the work. See, this is the hard work. This
Beta is a
just algebra.
constant.
Hmm?
Beta is a constant. I mean,
Okay. So it's measurable.
No, beta's a number.
Nice.
Beta's 0.8. Zero, you know what I mean? Beta's just a number, yeah. You know, if beta was random, then I couldn't take it outside. But beta's just a number. 29.08, right? So it's, yeah, so once we do this hard work, the rest of it's just plug in nothing.
Maybe think of it this way, before the blue, your distance between your x0 and xt is t. And so it doesn't matter if it's negative t or 0 or negative t over 2.
I get that part.
So that's just the same no matter what. And then you're multiplying that by beta over t. So it doesn't matter.
So is F0 all of the time from negative infinity?
That's a 0, yeah, but it doesn't actually matter. I said that it actually doesn't matter. This is true, even if F0 is just even a 0.
You can do that, when
We-
things
we
are
make that
measurable, you
difference.
can take them in or out, because expectations are linear operators.
No, because this is still, as long as X0 is.
So you can break them down. If you're adding a bunch of expectations, then they will see expectation not to be this.
It's a markup property, so this is equal to the initial expectation given just X0 or everything else. But I'm missing a step, right? I told you that the eligibility vector that comes up in TD1 possibly no 2. And why is that TD1?
That shouldn't be 5, shouldn't that be zeta?
No, it's 5. Oh, zeta's the term. Yeah, thank you. I changed the notation. Yeah, thank you. It's my old notes from 2014. I used a phi way back when, which was very stupid. Let's go phi. So zeta is eligible. So let's go think, but why is this? Damn. One second, everybody. Well, forgot to do some unraveling now. I'm not going to do it. There's an algorithm. Hold on a second. I'm going to give you, can I erase this now? We'll study this
Yeah.
now. So one algorithm that comes out of this, hold on a second. Wait, this comes out. I'm not going to give you TD1, I'm going to give you a much better algorithm, which is just to implement this monster. Take Mn to be 1 over n, sum t equals 1 to n of psi of xt transpose. You know I'm doing that. I'm trying to estimate this monster out. Take Bm to 1 over n summation t equals 1 to n of c of xt zeta t, where zeta t's are old friend. I could shift again, but I could replace, this expectation wouldn't change if I placed 0 by 25 in both cases.
That's a capital C or that's a lowercase?
That's the thing, the old friends, there's no belief states or
Right.
anything like that. All right, so it would be a little bit more work to unravel this and show you it's a matrix gain version of TD1. It's actually just my new graphs and improved version of TD1. The convergence is the same thing.
Does it have a name?
Well, this is called LSTD. Yep. And the people who wrote the paper on LSTD learning, they didn't know anything about variance. You know, it is, it's LSTD.
It's not the same.
But it's the same thing.
Oh,
LSTD1.
okay. And I think they would.
The LSTD lambda they have. The LSTD is that. I think it's John. Forget it. I'll put the LSTD there. There's an LSTD lambda, which is a matrix gain version of TD lambda. But LSTD1 is LSTD. And that's that. And so this turns out to be like the stochastic Newton-Raphson version of TD1. And I'm still so confused about the history because the people who wrote the paper on least squares temporal difference learning weren't thinking about variance or anything. They assumed that the true value function was in their function class. And they were trying to do, least squares corresponds to actually projections, you know, to try to get those. They didn't realize what they were doing was the minimum variance gain put on top of TD1. And the same with their LSTD lambda. It's a stochastic Newton-Raphson version of TD lambda. But the thing is that because all we've done is this, if you do the work, I won't do it for you, that will take a bit of time. If you do the work and show that this is just exactly TD1 that with a matrix gain dynamic, maybe I don't have time, but it converges the same thing. So the limit of this is the same as the limit of TD1. Stochastic Newton-Raphson. Yeah. So we put this the matrix gain in place to minimize the error. I'm mad at myself.
Before you erase
Yeah.
that part, the zeta part, on that side of the board. The zeta of 0 is the iteration number, right?
Where do you say I pass zeta for low pass filter, this is a low pass filter, and look at the answer comes there. That's how you would have defined the algebra. If you let it run forever. I mean, obviously you don't go from 0 to infinity, you don't go from infinity, it's fine. But if you could.
Could you repeat it, please?
The definite, I won't repeat it. There it is. You agree that's the,
Yeah.
that's the definition of the eligibility
Yeah.
vector when lambda equals 1.
One, yeah.
If you let this run forever, if you actually been running this from the beginning of time, you would get exactly that sum. That times that's all. And I have to convince you all, and I wasn't prepared to do this, that m theta star equal t is the TD1 solution. And I feel terrible that I haven't.
How have you not? Like,
Yeah, I mean,
that,
got it.
that equation
Okay.
is like the minimization.
Is it? Okay, cool. The thing is that I didn't bring notes on this, and so suddenly I can't think, how is it obvious? So tell me, how is it obvious?
We have to
Well,
change
we
M.
started from it with the
Yeah, we
linear parameterization, we got the quadratic program,
Yeah.
and that's the answer to the quadratic
There's a
program.
quadratic program, but why is it the same as what you get with TD1? That's what I mean.
So,
it is, though.
Why is this algorithm is like that algorithm?
So it's clear that it's the, we solved the minimum norm problem, but I claim that this is also what you would get with TD1. And
With these, the BIs are like corresponding to TD1.
yeah, but M is not. Like M, you have
M is not.
zeta in that term.
but,
The BIs are like the TD1 solution.
but actually,
Not very good.
let's have fun. Let's see if it's obvious. I can kill this. Just 1 minute, okay? I'm not wasting time. You know, let's expand this out one more time. This is the expectation of psi of xt, psi of xt, transpose theta minus B. No, it's not obvious, is it? Oh. Okay, well, so I guess that's the extra 20 pages and then I've already done. But it's not, I know, the thing is that you have to go the other direction. It's trivial to show that if you do a stochastic interruption implementation of TD1, you will get this algorithm.
The M wouldn't be the same, I think.
What?
The M, you wouldn't get that M, right? Like if you did SNR of TD1, that matrix would
Yeah.
be like zeta.
You might have a +1 or something. It'll be, no,
like,
it's the same. Oh, no, this is stochastic interruption of TD1, I know that.
okay.
Yeah, it's in my book.
Okay.
It is, it's in my networks one. What is it proof? It's very short, it's in the networks one. You take TD1 and you estimate the matrix inverted, whatever, you will get those.
But then it is LSTD1, right?
Yeah, there it is, it's just that I thought that the fixed point equation would pop right out of this. Because TD1, TD1, at first glance, the Galerkin approximation isn't that. It's, what is it? This is worthwhile. I look at the Galerkin relaxation, I have, what is it, everybody? It's C of xt plus beta h of xt plus 1 minus h of xt, all with betas, times zeta t, that's TD1. And to show that that fixed point equation and that fixed point equation are identical takes some muscle. They turn out to be the same thing.
So can't you?
Well, you can see part of it right there. This times this, and this times this, it all unravels. I don't want to do it.
When we did TD1 the first time, it was like with this. It was like with reference to the Q function as opposed to H.
Now, 2D, no, TD lambda, we started out with just,
We started with H.
yeah, but there's no TD lambda, there's no TD for Q lambda.
Well,
It's sort of the same, it's the,
like replace those H's with.
I take that back, but you don't get a linear algorithm like this. So for Q learning, you can never do this analysis because your fixed point equations are normal.
We did it.
Here,
The TD was with it.
here we have a linear
I just didn't know.
equation we have to solve. The Q linear is not linear. So that's what's wrong. All right, these turn out to be the same. If they start solve that, they start solve that, or identical. And that would take another half hour. We're not
I
going to do
take.
So if we, I think. Let's see, it's 16 equals 0. If you start with the quadratic program, that problem that we're trying to solve at the beginning, that expected value, difference between h and h theta, you kind of just remove the expected value there.
No, right there, the expectation's right there.
Oh, I know, I'm not saying you did that. I'm just saying like, let's see. So we expanded that quadratic form and then we kind of worked on each term individually.
Yep.
Just kind of like looking at a derivative using the chain rule instead. Take the derivative with expected data, you get the chain rule instead. You kind of get something that looks more like the TD1 that you've written below. You get, just without this, you get like two times.
If we'd done some dumb stochastic approximation algorithm of a fixed point equation of this, we might have quickly gotten to a TD algorithm. If we take this equals 0, you could stupidly just apply stochastic approximation. That's not quite right. Because you can see here, the eligibility vector multiplies everything. And here's just multiply this, it takes some. Okay, that turns out all this thing. All right. So I gave you the juicy parts. I didn't give you the one manipulation. And you've got to know there's nothing to this. So there's one smoothing property trick, and you can solve this thing. I don't know. To me, it was so exciting when I first saw this. The fact that you could use this. And there's some nice math here. So some of you like linear algebra. What we've done is we can start to imagine that. Basically, you know, H is an operator of C. And what we did, we can start to use that joint. That's what we did. That's been that concept. You know what the algebra is? So, what to do? Some of you have to pee, I guess. We should take a break for a few minutes, and then regroup and decide. I think I can give a pictorial, you know, just the main idea of how to read the convergence proof. And the plan is either I go through the whole thing at night or on Tuesday, or not. We'll decide. But I started to set things up for you already. Right? We have and there is only one method. I mean, the OD method, I've never seen another method. And what that means is that we're trying to show that in some sense, the sequence of iterations approximates the solution of OD we started with. So we have our own. And unfortunately, we have to stick to this limitation here. I use W here. I'll stick to this notation. Okay. So this is 0 to me. So this, you know, in applications we looked at as a Markov chain. In these notes, I assumed it was IID, which doesn't fit in the course of because you always have a Markov chain here. The conclusion here that this is something nice holds for Q linear beautiful. Now, I'm not going to give you the mathematical assumptions. It would take 20 minutes to give you the assumptions. It's much better to give you a big picture first. Okay, so that's that. And then there's like an ODE. And the question is, how on earth could you ever hook up that and that? How can you relate a discrete time recursion to an ordinary differential equation? And at least getting that in your head is important, just to see how you think about that. Again, there's some notation mismatches in these notes because these were developed in different times. But the main first step is, I'm going to forget what the details of this saying. basically, there's a set H, say maybe it depends on the initial condition, maybe it's random, I don't care. But it's some bounded set, bounded. So this guy could be unstable, it could be x equals x, blows up, x equals x squared, find its escape time. Obviously, this could be unbounded, this could be unbounded. But we're going to assume this is stable, and it turns out that this is stable under very mild conditions. This is stable in the sense that you can prove trajectories are bounded. And if you look at the notes, you can see a theorem of that effect, and we'll leave that out. All right? So if this is stable in a suitable sense, you can actually deduce stability in stochastic recursion. That's a result of myself and the effect Borchardt, and it's used as a workhorse in this area. All right, and again, it would take too long to explain the details, but so how do you relate these together? Well, you do it by integrating. So I can't talk about derivatives here. I mean, there's a superficial relationship, obviously. I've got a difference. Looks like a dt, but that's no good. You've got to integrate both sides. So you have to. I know that if I write this in integral form, the x of t is the initial condition plus an integral, I have more hope of trying to connect it. All right, so you assume that the stability of the ODE What? What?
No, I was just looking at it, global asymptotic stability.
Of the ODE, yeah. You think that's a strong condition, but it won't work really well. So this fails, it doesn't work. So if you don't have this, no theory.
If you're assuming global asymptotic stability.
Of the ODE,
Of the ODE.
that's a design choice. So
Oh,
we're going to
okay.
design this ODE, so it's really, really nice. And that's the first thing. So actually, that's actually, since you guessed, 2 is F is Lipschitz, globally Lipschitz. Okay, so assumption 1, essential, absolutely essential. And it's kind of obvious. I mean, I'm trying to say these guys are so close to each other. Well, this is some random recursion. It's going to get big. You've seen it in your simulation. And if the OD doesn't recover, it's not going to recover. So you need this. If you don't have it, you can project. But even then, this is dangerous. You get stuck in the boundaries of where you're projecting.
Isn't Lipschitz not just fine, it's got to be under a specific constant?
Well, that's a constant. Whatever that supreme is, I'll call it.
Oh.
So you guys are pretty defining.
I didn't want to have to, it was easier for me to write this way. So this is also, unfortunately, really essential. Now, anybody who knows about solutions to ODEs knows you assume the local Lipschitz continuity to get a solution there. And global Lipschitz continuity is a bit sad. But the thing is, a lot of these algorithms, all you have to do is renormalize them. So sometimes, like, you'll get a quadratic, like this thing called, I remember one example with Borchardt, this thing called Oya's algorithm. Anybody ever come across that? What's it called? Oya? Oh, it doesn't matter. It has a quadratic nonlinearity. And all you have to do is divide by 1 plus the norm of x, and you can Lipschitz. All you have to do is scale it. So this isn't as bad as it sounds. Continuity is a bit of a shame. Yeah?
I'm just trying to see the parallels between the stochastic approximation and the ODE.
But
Essentially,
but I'm not anywhere near there. I'm telling you,
no,
properties of the
what
ODE.
I'm trying to see right
Yeah.
now is this f bar of x is the same f bar of theta.
Oh,
and
yeah,
theta
yeah, I
as
just-
being plugged
I
in.
need
That's
different
why we care about the
notation. I need different notation for the different.
ODE. No, that's okay. I'm
Yeah.
just trying to figure out.
Yeah, no, I mean, oh, I forgot the bars here. Sorry about that. I'm here for the bars. But yeah, I mean, I've got an ODE and I've got a first equation. X is an RD. And what's really unfortunate is the notes I use psi, and I'm gonna have to use some.
But
And an ODE, okay, I mean, I could put any symbol I want here, right?
that's okay.
Yeah, yeah.
But if you're assuming global asymptotic stability of the ODE,
Yeah.
that means that any input that goes into ODE.
There's no input, there's no input, no, this is, look, there's no input. There's no control here, this is not a control problem. This is about.
I mean a function, any x that goes into a function or theta n.
Xt is an RD. You know, just like theta is an RD.
You can see that we're
I
always
think
on this.
it might have been a mistake
Yeah.
with X.
No, because that's a global asymptotic stability of the ODE, which governs those dynamics, not theta dynamics.
Yeah,
It's x dot, when the derivative is equal to f bar of x, then it's globally asymptotically stable.
So that means x of t is globally asymptotic.
Right, but
It
the
is.
iterates don't necessarily match that. That's what we have to prove.
Okay.
The discrete time iterates don't.
So what
We
we're
don't
saying
know
is
that.
that theta, the thing that theta n
we don't know anything
converges
about
to,
this yet, right? I'm just talking about this ODE.
is globally asymptotically stable.
The
So
ODE.
they have something to converge to. That's what I'm trying to figure out.
Yes, right.
Oh, yeah, we still have we have our F bar theta star, that's always the goal.
Yeah, because we can't say that they go to the same point if x goes up to infinity.
So when I say it's globally asymptotically stable, I mean to the stationary point. So Xt. Right?
The theta that you're using there just says like the dummy variable.
Yeah, but I'm just taking the supernumeraries there, I could have X and X bar.
Yeah, use x and y.
Yeah, yeah, I mean, that's, yeah. I mean, I know that notation puts in context. You see X, you think of a state variable. It's really a pain. There aren't enough letters in the universe.
I understand now.
Yeah, okay, cool. But so here's what you do, is that, here's how you use, here's how you use these assumptions. And we don't have a lot of time, but I just want to give you the picture. What I'm going to do is I'm going to come up with two processes. And I did this very briefly when I talked about central limit theorem. So, okay. Now, actually, I have to wait on how I define T. But in the end, I have a big T. I'll make this formal alone, but basically, for the ODE, if I start anywhere in that bounded set H, after T seconds, I basically can start. I'm within some micrometer of theta star. No matter where. That's one of the big tricks. I'll make that precise in a second. But actually, I want to say something else. I want to construct two processes. And this is insanely ambitious. So we saw before that so in the notes I use psi, unfortunately. again, dot, 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 I have to define my time. So if I'm gonna try to match up solutions in ODE with this is in discrete time, this is continuous time, somehow I have to compress integer time here to match up continuous time here. And the way to do that is this, is to define a time, a change of time for the discrete version of this form. And I'm going to define psi of t to be equal to theta n if t equals tm. So at these particular times, I'm just going to pick off the theta n that I'm seeing, and just make it piecewise linear interpolation, continuous elsewhere. All right, and then I said I construct two processes. So one of them is just I construct my choice of time and I interpolate. The other one is a solution to the ODE, but done in a very clever way. This is the main idea that I want to get across. But would it make any sense to just say, to solve this, start the ODEs times 0 and watch them and see if they get close to each other? You guys have written this code, that's absurd. You know? So what you got to do is you got to keep trying. So you're gonna look for an ODE match, and it's going to be crappy. And you're going to wait that capital T seconds, you're going to try again. And you're going to wait again and try again. What's going to happen is you're going to finally get a better and better match, as you can make precise.
P means polynomial?
What's that?
Piecewise linear.
Piecewise linear, exactly. So basically just, and so what you do is this, is I gotta let, I'm going to construct, to do this I have to construct a sequence, that's another sequence of times. What I'm going to do is I'm going to take a sequence of times which the increments are always about t. And all the r's, I look at when the sum of the t, when are these tn's, the difference, I'll make it formal. Don't worry, all I have to do is make a few definitions and give you the main pictorial idea. So again, so I'm going to make T1 equal to the minimum of Tn such that Tn is greater than T. Right? So I've got this time thing going on, and Tn plus 1 and then I do it again. I look at the smallest Tn, which my difference is greater than T. Right? And then I can construct this guy. I solve this ODE, reinitialize it each time, trying to get lucky again. So So on each of these semi-open intervals, this new guy is going to be piecewise continuous. I solve the ODE, but I try again, I restart. Okay. So at time 0, this will suck. I'll start off the ODE, and I'll look at the recursions for my guy, and they'll have nothing to do with each other, because the theta ends are just rambling around. But as things go further and further along, it gets better and better. And here's the magic. So this is RD over here, okay? I can't draw all of RD. All right. And here's T1, and here's T2, and T3, and so forth. And there's also, under our assumptions, each of these distances is almost exactly 3, because of the way this is defined. And what happens, and then there's H somewhere. So when I reset, I'm always resetting in some bounded set H sort of time. It doesn't depend on time or anything, it's some bounded set. And what I'm going to do is, like here is my initial condition. T is big. I'm not going to throw epsilons and deltas to you, I'm just going to say it. If I started out here, and by T1, I can't see on the blackboard. The distance, I've got global atmospheric stability. I took T so large, and this was less than 10 to the minus 10. That's 0 on my computer. Okay? Right? No matter where I start, so T is so big, no matter where I start in H, I'll be basically dead on at the end of this interval. If they start, right? Some epsilons and deltas that are good. But there's an O there, because then I have to reset the damn thing. Okay, so all I'm drawing through here is the solution to the OGE. It's reset over and over again. And it's reset according to this interpolate process, which is going to look like this. It's going to do some crazy things you've seen. But it stopped there, and that's when you reset the ODE. Okay? And it doesn't reset. It's going to do some crazy nonsense. But it ended up there. I mean, you can't draw this, so that's psi of t. So psi of t is this noisy piecewise linear thing. And the ODE is always resetting itself. It starts where the stochastic model starts, was at the time. And it ends within that micrometer if they just start. And what you've got to do is then somehow connect up these two guys. And what you end up showing is that as I look at these windows that are going on and on, they solve the same equation basically. So I'll say this and then we'll quit. if you actually look at the recursion for theta, it's gone now. There it is. d theta equals f bar of theta dt. That was dt by definition. The t's are gone now. But what I mean by that is alpha n plus 1.
Okay.
The tn plus 1 minus tn is defined to be alpha n plus 1.
Okay.
Right? So if you actually write out what psi of t is, it's the initial guy plus the standard approximation and integral of a summation of f bar of theta n times the deviation of time.
But for early terms,
What?
don't we have it so that alpha is decreasing over time?
Yeah, that's right, exactly. But the thing is that Tn goes to infinity by assumption. That's a crucial thing. So Tn is the sum of the alpha n's, that goes to infinity. So even though that's what's so cool, is that the reason this works is we're getting a finite approximation as time goes on. The fact that these delta Tn's are going to 0, it saves us. It makes things easy. So the fact that alpha n is going to 0, so part of the error in the integration is from that. And part of it is from this noise term here, which is being multiplied by a small term. And that's where you have to get out some muscle and use some probabilistic arguments. But you end up showing that goes to 0. And then you found that you have psi hat of t is the same thing. And I made a mistake here on purpose. It's not a mistake. This is a definition of the solution in a differential equation, right? But I was very careful to not have a hat there. I initialized with this one node. And so now you can see what's going to happen is I'm going to take the difference of both sides and look at the error time t. And these will cancel out. And here's where the damn Lipschitz here's where the damn Lipschitz continuity comes in. You have to say that the difference between here is also in constants and normal differences. And that's it. That's it. That's really fun. And so you can see without that Lipschitz continuity, at least it has to be global in the region that you know you're stuck in. You know, and that's it. It really is it. So there's work to do in bounding this error term. But the whole proof is just that. And this really pretty picture that the OD keeps returning. So you know all you have to do is if you can make sure that the stochastic recursion is close to the ODE. Because after all, the ODE, if it gets reset close by, it's not going to go far away. That's part of the assumption. All right? That's the big picture, you know, with all the details. That's single epsilon and delta stated. All right? You see what I mean? So you've seen how you approximate a differential equation, you know, and Lipschitz continuity is used exactly, you know, in this way. You basically write an integral form and you try to control the area extension. Yeah. Okay. And so if we were, you know, if this was the beginning of the course in stochastic approximation, I'll tell you what the hard part would be is when that guy's zero mean function of Markov chain. Analysis gets really hard in dealing with this error term. But Watkins algorithm turns out to be a martingale difference sequence. Piece of cake. Those nodes are completely separate. You've got to prove this. Like other algorithms. This a zero function Markov chain. It's much, the analysis is much harder. That's all. I think that's enough. All right. So that's a lot of my lecture. So, I'm still waiting to get your choices on these projects. I think some of you, the ones I've gotten are so ridiculously ambitious, I don't know what you're thinking of.